So, we are looking at oblique shock waves and expansion waves, and we have looked at how to analyze oblique shock waves and expansion waves. Further on done a elaborate problem using a diamond wedge configuration in supersonic flow, and saw how you can calculate pressures at each region using the oblique shock waves and expansion waves. And now we will move on to a related topic: what happens when these waves interact with a wall. It is often found in engineering applications. You can have these shock waves and then the shock waves produced by say a 4 body can come and interact with the wall at a downstream location. So what happens at that particular interaction? So these are reflections of shocks and expansion waves. So we will look at reflection. Before we go into reflection itself, it is useful to look at what are known as pressure deflection diagrams. They are a plot of all possible shock waves. Oblique shock waves also includes see the normal shock is a special case of an oblique shock. So, if you plot all possible shock states for a particular Mach number, the pressure ratio across the shock versus the deflection angle for one given. So, here a particular curve is for one given Mach number. The top one, the solid line, is that for Mach number 4, and the dotted line is for Mach number 2.5. And this kind of diagrams are useful when we look at interactions of shock with say solid surfaces. We will soon come to know what happens there and how these deflection diagrams, pressure deflection diagrams, can be useful. Now notice that you have a two sets of solutions for any given deflection. This we know for an oblique shock. For a given Mach number, any given deflection, there are two solutions. One is the, if I take say 15 degree, here there is one solution and there is a solution up here, and this is the weak shock solution. The other one is the strong shock solution. Pressure ratio for strong shock solution is much higher and Mach number is subsonic. So, this idea should be there. Also there are attached shock solutions only until the maximum angle, that is angle of deflection. So, that is why this curve has a maximum, that is at theta max. Beyond theta max, for this particular Mach number there is no solution. So, no attached solution, the flow the shock has to detach. So, you can draw these curves for various Mach numbers, and comparison is also given. All of them start with a Mach wave. So, the weakest possible oblique shock here is a Mach wave. So, you have that deflection angle there is 0, theta is 0, while the angle of the wave is mu, and the pressure ratio P2 by P1 is 1. The maximum possible pressure ratio is that for a normal shock for that given Mach number. Even there the angle of deflection is 0, and the pressure ratio P2 by P1 is exactly that for a P2 by P1 of the normal shock. So, these one should be aware of when one looks at oblique shocks. So, even for angle theta equal to 0, you can see there are two solutions. One is a Mach wave, the weakest possible oblique shock, and the other one is strongest possible oblique shock, that is a normal shock. And the maximum angle is represented here. For another Mach number it will be a different point theta. So, you should be aware of this pressure deflection diagram. It is often used to represent certain solutions when we look at interaction of shock waves. So, we will see and go ahead and look at reflection problem. So, when also one should be aware that the flow can be deflected. So, now if you look at the shock wave alone, okay, the flow is deflected towards the flow, that is the incoming flow. So, this is theta. Now, if you consider the incoming flow, the theta can be deflected either left or it can be deflected towards the right. So, the shock can do the leftward deflection or rightward deflection. So, accordingly shocks get classified, they are known as families of shocks. If it deflects the flow towards the left of the main flow, then the shock is known as left running shock, and you can see that the shape of the shock itself is different from on both sides. They have the same angle beta, but the way they produce deflection is different. So, this is right running shock, it deflects the flow towards the right. So, so all left running shocks form one family, all right running shocks form another family. But if they have the same angle beta, so the pressure ratios across these shocks are the same, P2 by P1 across both these shocks will remain the same, because the angle that the shock makes with respect to the free stream, this mainstream direction is beta. But the flow deflection, if I consider the plot, one case, say if I take the left running shocks as positive, so this is theta positive, and if I take right running as negative, theta, this is negative, then pressure deflection diagram P2 by P1 would look symmetric across this. It would be of this some kind here, this is 1, this is the normal shock, and it will be symmetric because pressure ratios remain the same. So, this understanding one must have, and when looking at shocks and their interactions, you should always check whether it is left running or right running. Okay. So, now we come to reflection of shock waves. Now, this has to be clearly differentiated from reflection of sound or light or such kind of waves. These light waves or sound waves are they are governed by the linear hyperbolic equations, and their reflections follow the laws of reflection of light. You very well know this. If it is a specular reflection, it is a mirror surface, then angle of incidence equal to angle of reflection. You know this very well from basic physics. Do shock waves follow the same thing? No, they do not. So, shock wave is not a wave in the sense of a sound wave or a light wave. So, the shocks do not follow these equations that theta 1 equal to theta r. Rather, the way to analyze the shock wave reflection is to look at each shock, that is, this is the incident shock. Okay, it is coming and impinging on the surface, and then there is a reflected shock, okay, reflected wave. Now, a flow is happening. Now, how would we analyze this problem? The problem has to be analyzed by looking at each shock separately, looking at conservation equations across each shock. So, each of them is an oblique shock. So, this shock turns the flow towards the wall. So, you get a supersonic flow now that is turning towards the wall, but the wall is a boundary, it cannot allow flow to go into it. So, because of that no penetration condition, you get a reflected shock wave which again turns the flow back parallel to the wall. So, this is the concept here. When we talk about reflection of shock waves, please do not confuse it with already known things about reflection of waves, and follow the ideas like angle of reflection is equal to angle of incidence. So, that is not true for shock waves. So, shock waves you have to do the analysis. that is important. So, we will see how to go about doing it. Now, if you look at the waveforms formed during reflection. So, shock wave is not a they do not follow any linear principles, they are completely non-linear. So, they form many different reflection patterns. One pattern which was just now we were describing is here, it is called a regular reflection pattern. This happens when the incident shock waves are quite weak for the given Mach number. Then the pattern that is formed is you have an incident shock. In order to match boundary conditions at the wall, a reflected shock is formed, okay, and we have to do the analysis to get what are these angles beta 1, beta r, and what are the properties at 0, 1, 2. This analysis has to be done, carried out, but the formation is that of you have an incident wave and a reflected wave. But there are certain situations you can see when the incident waves are quite strong and they come and are incident on a wall, then situation can so happen that this solution that we have here is no longer possible. It is no longer possible to satisfy all the boundary conditions at the wall. So, then as a consequence you get another kind of waveform. This kind of waveform is called a regular reflection. When we talk about reflection in this course, mostly we will be dealing with regular reflections, but one should be aware that there are several others. Regular reflection is only a special case. There are several other kind of reflection patterns, and one kind of a pattern involves these three shocks, that you have an incident shock, you have a reflected shock, and you have a what is known as a Mach stem. Here at the surface, this is normal to the surface. So, it is at the surface, if you have a streamline here, it is a normal shock for this streamline, but reaching close to this point where the three shocks are meeting, it is called a triple point. So, it is T. So, you have the same M0 actually coming here, so it is M0. So, now you see that M0 for this particular stream, the M0 passes through two shocks, okay. So, it passes through two shocks, that is incident shock and reflected wave, but an M0 coming here passes through a single strong shock over here. So, then region 3 and region 4 they will have differences. We know there is a virtual line here which is the slip line. Boundary condition here is that across the slip line P2 should be equal to P3, that is pressure should be equal. At the place where the slip line leaves, the angles of these two should be they are parallel to each other. So, that is the conditions that we have, okay. This kind of a structure is known as a Mach reflection, but it is a one particular case of irregular reflections. There are many kinds of irregular reflections. So, we will not go into too many details of all kinds of irregular reflection, but this flow picture one has to be aware of, that there are regular reflections and there are irregular reflections. So, how do you analyze these reflection patterns? You do form, so that is what you have to solve between region 0 and region 1. So, this is the set of equations that is written for the oblique shock between region 0 and region 1. Similarly, you have to write set of equations for the regions 1 and 2, okay. So, these are the regions 1 and 2. So, you write separate set of equations between them, and you have the boundary condition at the wall that the flow remains parallel to the wall after all these interactions. again it becomes parallel to the wall. So, initially it had a deflection theta 1, the same deflection in the opposite direction has to be given. So, this is theta 2 and theta 1 equal to theta 2. So, what you have here is a series of such equations, and you have 9 equations here and 13 parameters, and you need to know certain parameters. 4 parameters should be known to solve this problem, and you do not have all same, so you do not have any unique solutions. So, there are non-unique solutions, and usually 2 physical solutions are possible. So, this is how to do it analytically. We will see a better way to look at this is using the pressure deflection diagrams. For the irregular reflection also you can do the same kind of analysis. Okay. So, now you have these relations across the incident shock, across the reflected shock, and across the Mach Stem. So, you can write they are all oblique shocks, you are doing the analysis at the triple point, and P2 equal to P3, that is known. Okay. So, this is known, and then you can apply the boundary condition here that the flow should be parallel. It depends on how the angles are deflected. You can have either theta 2 theta 1 minus theta 2 or theta 1 plus theta 2 is equal to theta 3. So, these conditions can be given. Again the number of equations is large, you have 14 equations, 18 unknowns, and again this is a case of non-unique solutions. This is how to do it analytically. It is quite involved. So, largely what people do is look at shock polars. Now, these shock polars can be drawn for each region. So, because the shock polar is a plot of all possible shock waves, you can look at the shock polar and try to find the solutions. So, the incident shock, so given a particular incident Mach number and an incident shock, you have all possible shock waves for that Mach number is given here. You know the incident shock value, so you know what deflection it has given. So, this is the point that is region 2 for the incident. So, if I take region 0 and region 1, so this is the incident shock and this is the reflected shock. So, this is region 0, M0, and this is region 1. It has a certain flow deflection. This is known to us. So, it is known. Now, at region 1 we know the Mach number from the analysis of the first shock, what is M1. Since we know M1, we can plot all possible shocks from M1, and now you can see that these are the families of shock. So, this was one family of shock, but now the reflection is the other family of the shock, and all possible Mach numbers, all possible shocks can be plotted. It is another pressure deflection diagram, and we know the boundary condition at the end that theta should become 0 again. Initially it was 0 and then finally it is 0. So, we seek a solution where theta equal to 0, and we find there are 2 such possible solutions. One is a weak solution, the other is a strong solution. So, this is how we can effectively use the pressure deflection diagrams to look at such interactions. Similar solution can be done for even the Mach reflection. So, in Mach reflection you find that the second shock polar that is drawn does not intersect with the theta equal to 0 curve, but rather at a certain location here on the main on the m equal to 0 curve. So, M0 curve, and that gives the condition theta 2 equal to theta 3. So, this is the solution for a Mach wave, irregular reflection kind of a problem. This kind of solution. So, shock polars can be drawn for such kind of problems, and they give a graphical and visual means to look at these problems. Okay. Now, just a note that we were talking about regular reflection and irregular reflection. So, why this kind of differences occur? There are several possible reasons why these occur. One of them is that we know that if you look at any oblique shock problem, then there is always a maximum angle beyond which you cannot have attached solutions. The regular solution or regular reflection is like an attached shock problem, that the shock is attached to the wedge. But what happens when I continue to increase the angle of deflection, so that for the Mach number in region 1 M1 I am beyond the maximum angle, which is the case here in the irregular reflection. See, this angle is much greater than the one for attached solution. You needed attached solution at theta equal to 0, but there is no such solution possible. Therefore, now the flow has to take another course and it takes the irregular reflection. So, this particular criteria is known as maximum deflection criteria, but in literature one can find many different criteria. So, this is just a note, and for people to sort of think about that there are such problems in shock reflections, and it is interesting to look at this nonlinear behavior of shock reflections. Another important feature of nonlinear behavior is hysteresis, that is the possibility that you can have multiple solutions, and in certain situations you will find one kind of solutions, in certain other situation you can find another kind of solution. And as you change the parameters, it is not necessary that the point where the switchover between one kind and the other kind happens remains the same. For example, this is a sort of a phase plot. You are having Mach number and the angle of the wall theta, or the angle of the wall, that theta wall, and you are looking at the reflection. So, there are two kinds of reflection shown here, regular reflection and Mach reflection. Okay, and what lies between these two curves? Okay, this is the region known as dual solution domain, where you can observe either Mach or regular reflection. Below this curve you always get regular reflection, above this curve you always get Mach reflection, but in between these two curves it is possible to see both of them. For example, while if you start off from point A and you are going to for a given Mach number, you keep increasing the angle theta w, you keep increasing the angle, then you might start getting Mach reflection from this point. So, you will observe regular reflection all the way until this point. But now if you start reversing the direction and start decreasing the angle, you can keep observing Mach reflection all the way until this point, and then only it turns to regular reflection. So, you see that this behavior is like hysteresis. It is a hysteresis that you can have regions where both these solutions can be observed, and it depends on the way you go into the history of the flow, whether you observe a Mach reflection or a regular reflection. Okay, so this is some interesting nonlinear behavior. Also, oblique shocks are quite different from the other waves. If you are able to give to the wall a certain angle such that it matches the angle that the oblique shock turns the flow with. So, it turns the flow by angle delta, and at this point of intersection with the wall is also turned by angle delta. Now, there is no requirement for the flow to do any further turn, therefore, you will not get any more waves. So, this is a method by which you can neutralize oblique shocks. So, no more waves will be formed here. Okay. So, also often in flows you find these virtual boundaries in the flow which have constant pressure. So, they are, you already saw a few of them, such as the slip line where you had P2 and P3, they are the same, but velocities can be different, V2 can be different from V3, or temperatures can be different, densities can be different, but pressure remains constant across these boundaries in the flow, virtual boundaries in the flow. And slip, they are usually referred to as slip lines. Now, if a shock interacts with the slip line, example of one, we will soon come across these in further classes, when a jet exits into a jet of high speed flow, supersonic flow exits into ambient, into the general ambient, then ambient has a certain pressure ambient, P ambient, but within the jet the pressure need not be the same as P ambient. So, for example, here you have shock waves. Shock waves are compressive in nature, they can increase pressure. So, P2 can be quite so P1 here in this case can be quite low compared to ambient pressure, P1 can be less than ambient pressure. So, as a consequence a shock wave is formed, so that at the boundary the pressure is maintained constant. Okay. So, in P2 the pressure is equal to ambient, but shock interactions can happen again with this boundary. So, there is another shock here P3. So, if this was P ambient, then at P3 pressure has increased again. So, P3 is greater than P ambient. Now, this shock comes and interacts with the free pressure boundary. So, when shock waves interact with the free pressure boundary, what should happen in the succeeding region? Actually, this region the pressure should remain constant, but across the shock pressure will increase. So, this was P ambient earlier. So, across the shock pressure will increase, but at the boundary pressure should remain constant. That cannot happen. So, as a consequence it generates expansion waves. So, shock wave, when it interacts with a free pressure boundary, it generates expansion waves. Okay. The vice versa holds good. Expansion waves, when they interact with the free pressure boundary, they lead to formation of compression waves which can coalesce together to form a shock. So, like waves, when like waves interact, the shock interacts with solid wall, it reflects as a shock wave. When it interacts with a free pressure boundary, it reflects as an expansion wave, it changes its character. Similarly, expansion waves, when they interact with a solid wall, they reflect as expansion waves, but when they interact with a free pressure boundary, they reflect as compression waves, and which further coalesce to form shock waves. So, this is important. So, distinguish between reflections from solid wall and free pressure boundaries like slip lines. So, this understanding is important. So, here we have completed our discussions regarding the reflection of shocks. We understood that it is not like sound waves or light waves, it is quite different, and you have to analyze each shock, apply boundary conditions at the wall, and only then you can solve this problem. And it is possible to have different kinds of waveforms at reflection. One kind is a regular reflection, which has an incident shock and a reflected shock. The other kind, a typical example, is a Mach reflection, which has an incident shock, a Mach Stem, and an incident and a reflected shock. So, that is a Mach reflection, and several nonlinear phenomena can be present there, like hysteresis, or you can even neutralize the shock if you provide the angle of the wall same as the deflection angle for the particular oblique shock. and if the shock waves interact with free pressure boundary, they reflect as expansion waves, and if expansion waves hit the free pressure boundary, they will reflect as compression waves which can coalesce to form shocks. So, let us look at some few numericals next class to understand this oblique shocks and expansion path.